Welcome to this video. In this video we'll explain one of the steps of the energy balance, the estimation of heat gains and losses through ventilation and infiltration. You will also learn about the different ways of ventilating and the requirements. As you might remember, the energy balance is built up from different energy flows: transmission, ventilation, solar gains and internal gains. In this video, we will focus on the heat flows through ventilation and infiltration. Ventilation and infiltration losses or gains are those amounts of heat which flow through the building envelope through air exchange. The heat flows are dependent on building characteristics like air tightness and ventilation openings and the indoor and outdoor conditions. For example, in this video we use two extreme weather conditions: very cold in winter and very warm in summer. Let's first consider the winter conditions. With an outside temperature of -5 degrees Celsius, as you can see, the indoor temperature is higher than the outside temperature, which means that if outside air enters the building, it will cool down the building. We will lose heat. In summer, when it's hot, the opposite is true. The outside air will be warm and heat will come in. How much heat you gain or lose due to ventilation is not only dependent on the temperature difference between inside and outside, but also on how much air comes in. But let's take a step back. Why do we ventilate? We ventilate a building because we need fresh air to remain healthy. Do you have an idea how much ventilation is needed to be healthy? It's around 25 to 50 cubic meter per hour per person. 25 is really a minimum. In many countries the regulations are in between these values. That is a lot. Let's take 49 cubic meter per hour per person. That's equal to a cube of 7 by 7 meter. That is much more than your lung capacity, for which you need on average 5 cubic meter per hour. This is because next to the heat needs for oxygen, the airflows in the building must remove all kinds of indoor pollutants like CO2 produced by breathing, odors, humidity produced by body and VOCs, volatile organic compounds, from construction materials and furniture. This is also why big buildings always have giant air shafts, as you see in the picture on this slide. Because it is tremendously important to have a healthy indoor climate, these ventilation airflows should not be reduced. Maybe in the future we will have well applicable ways of cleaning indoor air by which less fresh air could be used. Think of applications with UV light, for instance. But at the moment it really cannot replace fresh air. Unfortunately, because fresh air results in large heat gains or losses. Now, at the start of this video we mentioned ventilation, but also infiltration. What is the difference? In buildings we consider two types of airflows: infiltration and ventilation. Ventilation is controllable. You trigger it by, for example, opening the windows or turning on ventilation systems. This is the definition we use in this course. But be aware that in some calculation models or building codes, natural ventilation systems like window opening are accounted for as infiltration. Infiltration is what is non-controllable. The air enters the building through cracks in the building. And there are cracks in almost every building, but especially in older buildings. They are often occur in the connection between window frames and walls, between roofs and walls, and also through, for example, bricks. Bricks are porous materials, which means air can come through them. There are only 4 ways of ventilating a building. The first one is natural ventilation, such as opening a window or by ventilation grills. In most modern buildings you have a grill or a vent above the window that you can open or close. This system works only well if you have enough wind pressure difference between the different sides of the house. And so it happens very often that it's not ventilated enough. That is why we try to assist the ventilation by a ventilator. That's what we call mechanical ventilation. You can place a ventilator, a fan, to push the air out the building. It creates an underpressure in the building, by which outdoor air automatically comes in. That is what we call mechanical exhaust ventilation. Instead of pushing the air out of the building, you can also use a ventilator to push the air in the building. It then creates an overpressure in the building, by which the air automatically goes out through the chimney or window window grill. And finally we have the balanced system, in which there are two ventilators that arrange both supply and exhaust air. The main advantage of this system is that you can make use of heat recovery system. This is called heat recovery ventilation and has applied for decades in many air handling units in service buildings. The application in residential buildings is more recent, but is becoming more standard now in North European new builds. Let's take a closer look at how it works. Let's start with the cold season. The incoming air in the winter is cold and must be heated by the heating system to the desired indoor temperature. However, the air leaving the building is warm already, and it's a big pity not to recover the heat and to just throw it away to the outside. The heat exchanger makes it possible to recover the heat. The warm exhaust duct is placed very close to the cold air supply duct, by which heat goes from the warm duct to the cold duct, preheating this way the incoming air. This will reduce the ventilation losses significantly. And the advantage of this system is that the airflows are really not mixed, which would pollute the incoming air. Only heat is exchanged. In a hot summer situation, the heat exchanger can be used the same way to pre-cool the warm outer air, which is maybe around 35 degrees Celsius, with the cool indoor air, which might be only 25 degrees Celsius. This heat recovery system is a good example of reuse of waste heat energy inside the building, which is part of the first step of the three-step strategy. If you have to decide on a ventilation system suited to your building, you could take the aspects of this slide into account. As we explained, mechanical supply and exhaust is often the most energy efficient, because it has the option to use a heat recovery system. The disadvantage is that it needs double ventilation ducts. Ducts that supply air and ducts that exhaust air. This requires a lot of space, which is an aspect that you should take into account. Further, there are the ventilators. Those make noise, some more than others, and it's essential for the comfort of the occupant that the noise level is as low as possible. So the choice and location of these ventilators in the building is extremely important. Additionally, these systems are generally equipped with filters that must be changed or cleaned regularly. Otherwise, the indoor air quality could decrease drastically. For buildings with a mechanical exhaust or supply, only a one-way duct is required, which reduces the required space, but is less efficient because heat recovery is not possible. And finally, we have natural ventilation, which does not require any ducts. Especially old buildings often depend only on natural ventilation. This was possible because the air tightness of those buildings was often poor, which made that the building got enough fresh air when enough wind is available. Although, because infiltration is not controllable, the heat exchange in natural ventilated buildings can cause discomfort and high energy losses due to infiltration. However, by careful design of natural ventilation, a lot is possible, also in service buildings. This asks for good knowledge of airflow modeling, and the design should be tailor-made. There are also more modern alternatives to prevent ventilation losses. On this slide you see an example of the double skin facade. This facade has two windows with a relatively large cavity in between. The The air between those windows can be heated up by the sun before it enters the building. This will work better in cold but sunny climates. When it is hot, a solar blind can be placed in the cavity. Now you know how to ventilate a building, which systems there are, and how much ventilation is needed for a healthy indoor climate. To make the energy balance, we also have to calculate how much energy we lose or gain due to ventilation and infiltration losses. If you want to calculate the heat loss due to air change, you have to sum up the mass flow due to ventilation and infiltration times the CP, the specific heat of air, times the temperature difference between outdoor and indoor air. If you apply a system that uses heat recovery, the second formula should be applied. You see that there is an efficiency term, eta, coming up. This eta is the efficiency of the heat recovery process. Generally, this lies between 0.6, which is very poor, and 0.9. This heat recovery only works if the temperature difference between indoor and outdoor air is higher than 2 to 5 degrees Celsius. In very good systems that you see nowadays, the difference around 2 degrees Celsius is enough. Let's concentrate now a bit on the variables in the equation. First, you have noticed that in the equation a mass flow rate was used in kilogram per second. However, when we talked about the quantity of fresh air needed earlier in this presentation, we expressed it in volume flow rate, cubic meter per hour. So you have to go from cubic meter per hour to kilogram per second, using the first equation. When we work with infiltration, the unit ACH is used a lot. ACH stands for the air change rate. 1 air change per hour is the same as 1 indoor volume of the building being refreshed in 1 hour. So, if you have a building with a volume of 100 cubic meter and I have an infiltration of 1 ACH, it means that I have 100 cubic meter air change per hour in that building. If the ACH is 3, the airflow rate will be 300 cubic meter per hour. What is often forgotten is that also the ventilators require energy, electricity. The equation above shows how to estimate the electricity use of the ventilators, using the so-called ventilator law, which says that the power needed by a ventilator or fan is equal to the volume flow rate of the air to be moved times the pressure losses in the system by the friction in the ducts or bands divided by the efficiency of the ventilator and its motor. As for the pressure drop, for quick calculation, you can estimate that in small buildings they would be around 200 Pascal for a single ventilator. But this can increase too much more for a large building, let's say up to 100 Pascal. This electricity is not being included into the room balance for heating and cooling, but it should be taken into account while calculating the electricity needs of buildings for appliances. In summary, this video explained the difference between infiltration and ventilation losses, and the importance of ventilation for your health. You are now able to estimate the heat losses and gains through ventilation and infiltration for a simple steady-state situation. And you can explain different types of ventilation systems. Finally, you are also able to estimate the electricity consumption of a ventilator, which is an aspect that's often forgotten.